The Jacobian determinant is a single number that measures how a multivariable function stretches or compresses space around a point. Imagine a small rubber sheet with a grid drawn on it. If you apply a transformation like pulling, rotating, or shearing the sheet, the tiny square at a point may become a parallelogram. The area of that new parallelogram divided by the original area is exactly the absolute value of the Jacobian. Mathematically, for a vector-valued function f colon r superscript n to r superscript n with components f sub 1 through f sub n that depend on variables x sub 1 through x sub n, the Jacobian matrix is the matrix of first-order partial derivatives. J of f equals a matrix whose ij entry is the partial derivative of f sub I with respect to x sub j. The first row is partial f sub 1 over partial x sub 1 partial f sub 1 over partial x sub n. The last row is partial f sub n over partial x sub 1 partial f sub n over partial x sub n. The Jacobian determinant, denoted det j of f or simply j, is the determinant of that matrix. It tells you locally how volumes or areas in 2D change under the mapping. The Jacobian can be thought of as a multi-dimensional version of the derivative of a single variable function. While the ordinary derivative gives the slope of a curve, the Jacobian gives the best linear approximation to a mapping in all directions at once. To compute a Jacobian for a transformation involving two variables, write the transformation as x equals x of uv and y equals y of uv. Then form the 2 by 2 Jacobian matrix of partial derivatives. J equals partial x over partial u comma partial x over partial v semicolon partial y over partial u comma partial y over partial v bracket. The Jacobian determinant is the area scaling factor. Determinant j equals partial x over partial u times partial y over partial v minus partial x over partial v times partial y over partial u. Example, convert Cartesian coordinates x comma y to polar coordinates r theta using x equals r cosine theta, y equals r sine theta. The Jacobian matrix is cosine theta comma negative r sine theta semicolon sine theta comma r cosine theta bracket. So the determinant is r times cosine squared theta plus sine squared theta equals. This tells us that a small rectangle d theta in r theta space corresponds to an area rd theta in xy space, exactly the familiar area element in polar coordinates. A practical analogy: imagine a rectangular piece of graph paper. If you stretch it more in the u direction than in the v direction, the Jacobian tells you how much the square inch on the paper has become a parallelogram in the xy world. Explanation: when evaluating a double integral over a region that is easier to describe in a new set of variables, the Jacobian appears as a correction factor. Suppose you want to compute double integral over r of f of xy dx dy, but you change variables to uv with the transformation x equals x of uv, y equals y of uv. The integral becomes double integral over s of f of x of uv, y of uv, absolute value of det j of uv du dv. Where s is the image of r in the uv plane, and absolute value of det j is the absolute value of the Jacobian determinant computed in the previous step. Real-world picture: think of pouring water onto a flexible membrane that is being deformed. The amount of water that lands on a small patch of the original membrane is the same as the amount that lands on the deformed patch, but the shape of the patch changes. The Jacobian tells you how the size of the patch has changed, ensuring that the total volume integral stays the same. Example, evaluate double integral over r of x squared plus y squared dx dy, where r is the unit circle. In polar coordinates, x equals r cos theta, y equals r sin theta, and det j equals r. The integral becomes integral from 0 to 2 pi of integral from 0 to 1 of r squared times rd theta equals integral from 0 to 2 pi of integral from 0 to 1 of r cubed drd theta equals 2 pi times 1/4 equals pi over 2. Explanation: for three variables the idea is the same, but the Jacobian matrix is 3 by 3, and its determinant tells you how a tiny volume changes under the transformation. If x equals x of u v w, y equals y of u v w, z equals z of u v w, then J equals a 3 by 3 matrix with first row partial x with respect to u, partial x with respect to v, partial x with respect to w. Second row partial y with respect to u, partial y with respect to v, partial y with respect to w. Third row partial z with respect to u, partial z with respect to v, partial z with respect to w. And the Jacobian determinant, det J, is the volume scaling factor. When you change variables in a triple integral over region R of f of x, y, z dx dy dz, to u, v, w, you replace dx dy dz by absolute value of det J du dv dw. Example cylindrical to Cartesian, let x equals r cosine theta, y equals r sine theta, z equals z. The Jacobian matrix is a 3 by 3 matrix with first row cosine theta, negative r sine theta 0. Second row sine theta, r cosine theta 0. Third row 0, 0, 1. So det J equals r, hence the volume element transforms as dx dy dz equals r d theta dz. Analogy, imagine a tiny cube of jelly. When you squeeze and stretch it into a parallelepiped, the Jacobian tells you the ratio of the new volume to the original cube. If the ratio is 5, the new shape holds 5 times as much jelly. Linearity in each column. If you add two functions to a single column of the Jacobian matrix, the determinant expands linearly. For example, if the first column is a plus b, then determinant of a plus b c d equals determinant of a c d plus determinant of b c d. This mirrors the ordinary property of determinants and is handy when a transformation is a sum of simpler maps. Multiplicative rule, chain rule for Jacobians. If you have two successive transformations, capital F from x to y and capital G from y to z, then the Jacobian of the composition is the product of the Jacobians. Jacobian of G composed with f at x equals Jacobian of G evaluated at f of x times Jacobian of f at x in determinant form. The determinant of the Jacobian of the composition equals the determinant of Jacobian G at f of x times the determinant of Jacobian f at x analogy. Think of two conveyor belts that stretch a sheet. The total stretch is the product of each belt's stretch factor. Sign change on row or column swap. Swapping two rows or two columns of the Jacobian matrix flips the sign of the determinant. This is why the absolute value is used in change of variables formulas. The orientation, clockwise versus counterclockwise, may reverse, but the volume scaling stays positive. Zero determinant. If any row or column is a linear combination of the others, the determinant equals 0. Geometrically, the transformation collapses the space onto a lower dimensional subset. For example, a plane becomes a line, so the volume scaling factor is 0. These properties allow quick checks. If you know a transformation is a rotation with determinant 1 followed by a uniform scaling by factor k, determinant k to the n in n dimensions, then the overall Jacobian is k to the n. A Jacobian is useful only when the transformation is locally invertible. The key condition is that the Jacobian determinant at a point must be non-zero. If det J of f at x0 is not equal to 0, the mapping f behaves like a linear isomorphism near x0. Small neighborhoods are stretched but not squashed to lower dimension. Implicit function theorem brief. Suppose we have an equation g of x and y equals 0 defining y implicitly as a function of x if partial g with respect to y is not equal to 0 at a point. Then locally we can solve for y equals h of x, and the derivative h prime of x equals negative the partial g with respect to x divided by the partial g with respect to y in higher dimensions. The theorem says, if f of x and y equals 0 and the Jacobian matrix of partial derivatives with respect to y is invertible determinant non-zero, then y can be expressed as a function of x near that point. Real-world analogy. Imagine a map that stretches a rubber sheet. If at a point the sheet is not torn, non-zero Jacobian, you can always reverse the stretch locally. You can slide a finger back to its original spot. If the sheet is folded flat 0 Jacobian, you lose the ability to recover the original position because information is lost. Consequences. Invertibility, a continuously differentiable map with a non-zero Jacobian everywhere on a region is locally invertible everywhere. If the region is also simply connected and the map is one-to-one, it is globally invertible. Change of variables. The absolute Jacobian appears in the integral because it compensates for the local stretching. If the Jacobian is 0 somewhere, the transformation would map a region of positive volume to a lower dimensional set, making the integral ill-defined. Explanation: many engineering problems are easier in polar, cylindrical, or spherical coordinates. The Jacobian tells us the correct volume or area element in these systems. Polar two-dimensional, x equals r cosine theta, y equals r sine theta. Jacobian matrix equals bracket cos theta, negative r sine theta, sin theta, r cosine theta bracket. Determinant equals r. Thus dx dy equals r d theta. Cylindrical three-dimensional, x equals r cosine theta, y equals r sine theta, z equals z. Jacobian matrix equals bracket cos theta, negative r sine theta 0, sin theta r cosine theta 0, 0, 0, 1 bracket. Determinant equals r. Hence dx dy dz equals r d theta dz. Spherical three-dimensional, x equals rho sine phi cosine theta, y equals rho sine phi sine theta, z equals rho cosine phi. Compute the Jacobian a bit longer. The determinant turns out to be rho squared sine phi. Thus the volume element is dx dy dz equals rho squared sine phi d rho d phi d theta. Intuitive picture: in polar coordinates, moving a little outward by dr expands the radius, while rotating a bit by d theta sweeps out an arc whose length is r d theta. Multiplying gives the tiny area of a sector, r d theta. Similarly, in spherical coordinates, the area of a small patch on a sphere of radius rho is rho squared sine phi d theta. These Jacobians are used constantly in fluid dynamics, flow through pipes, cylindrical, electromagnetics, fields around antennas, spherical, and structural analysis, stress in circular plates, polar. Basic determinant: for the transformation x equals u squared minus v, y equals 2uv, compute partial of x comma y with respect to u comma v and state the geometric meaning of its sign. Change of variable in a double integral. Evaluate double integral over r of e to the x squared plus y squared dx dy, where r is the region bounded by x squared plus y squared equals 1. Use polar coordinates and show every step including the Jacobian. Chain rule for Jacobians. Let capital F of u comma v equals open parenthesis u squared plus v comma uv close parenthesis, and capital G of x comma y equals open parenthesis square root of x comma natural log y close parenthesis. Find determinant j sub g. Compose f of u comma v using the multiplicative rule. 3. Variable transformation. Compute the volume of the solid bounded by x squared plus y squared plus z squared equals 4 and z greater than or equal to 0 by converting to spherical coordinates. Write the Jacobian and evaluate the integral. Invertibility question. Given x equals u cubed plus v, y equals u plus v cubed, determine the set of points where the transformation is locally invertible. Explain why the Jacobian determinant being 0 would break invertibility. Implicit function theorem application. The surface is defined by capital F of x comma y comma z equals x squared plus yz minus 5 equals 0. At the point open parenthesis 1, 2, 3 halves close parenthesis decide whether z can be expressed as a function g of x comma y locally. Compute the relevant partial derivative and Jacobian. Jacobian sign change. If a transformation swaps u and v, that is x equals v, y equals u, what is the Jacobian determinant? Explain how the absolute value appears in the integral formula. Coordinate system conversion. Show that in cylindrical coordinates the divergence of a vector field capital F equals f sub r hat r plus f sub theta hat theta plus f sub z hat z includes a factor 1 over r that originates from the Jacobian. Derive the expression briefly.